Hello and welcome to MOOC lectures on strategy and introduction to game theory. In this module, we are going to introduce a new equilibrium concept, that is perfect Bayesian equilibrium. Let us start with an example. So, we have a game and you can think of it as a variation of entry game. I would not stick to the payoff that I had used earlier, just I will introduce that there is a player 1 who can take one of these three action, and these three action are out, left or right. This is player 1. If player 1 takes action out, then game ends and player 1 gets 1 and player 2 gets 3. If player 1 takes action L or R, player 2 doesn't know which action player 1 has taken, whether it is L or R. But once player 2 takes one of these two action, then player 2 get to move and player 2 has again two actions. I will represent them by small L or R. Remember, this is these two nodes, this node and this node, they are in the same information set. So, player 2 gets to move and the payoff here are 2, 1, here 0, 0, here 0, 2, here 0, 1. First of all, let us notice how many sub games do we have. This game has only one sub game, the whole game is sub game of itself. We do not have any other sub game. How about game starting at this node? We cannot have a sub game starting at this node. Why? Because it is not a singleton, this node is not in a singleton information set. So, we have only one sub game in this game. So, let us first find out the Nash equilibrium of this game. Of course, when we are trying to find the Nash equilibrium, we have to ignore the sequential nature of the game. We will assume that players are moving simultaneously. So, what we have here, we will convert it in the tabular form, and player 1 can take either O, L and R, these three actions, and player 2 can take small l or r. And here if player 1 takes action O, then does not matter what player 2 is doing, the payoff is always going to be 1, 3, 1 for player 1 and 3 for player 2, and similarly we will get the payoff for all the boxes, and we will verify for 1. Like for example, if player 1 moves capital R and player 2 takes action small r, then what happens? We move in this particular manner and we reach to this terminal node, and the payoff would be 0, 1. Let us first obtain the Nash equilibrium. What would happen? How can we obtain the Nash equilibrium? Let us say player 1 believes that player 2 is going to take action L. What would be the best response from player 1? Let us see. If player 1 takes O, then payoff is 1. If player 1 takes action L, then payoff is 2, and if player 1 takes action R, then payoff is 0. 2 is definitely greater than 1 and 0. So, player 1 would take action L. So, let me underline it to show that this is the best response. If player 1 believes that player 2 is going to take action R, with the same logic we figure out that O is the best response. So, we have obtained the best responses of player 1 given his belief. Now, let us do the same thing for player 2. Let me change the color. If player 2 believes that player 1 is going to play O, then whether player 2 plays small l or small r, his payoff would remain equal to 3. So, both would be the best response. Similarly, if player 2 believes that player 1 is going to play capital L, then the best response from player 2 would be L, because playing L would give 1 and playing R would give 0. If player 2 believes player 1 is going to play capital R, then L is the best response. So, clearly we have two Nash equilibrium. Here we get L, L and O comma R. Okay. Now, let us pay little bit more attention to this game, but let us look at the sub game perfect equilibrium of this game. How can we get the sub game perfect equilibrium of this game? This game has only one sub game. So, mass equilibrium of this game would be also the sub game perfect Nash equilibrium. So, L comma L and O comma R are not only Nash equilibrium, but they are also sub game perfect. NE and SPNE both are the same. But now, let us pay little more attention to this particular game. Let us focus on this information set where player 2 has a move in the game. When player 2 gets to move in the game, no matter where he thinks player 1 has taken action L or player 1 has taken action R, his action small l strictly dominates his action small r at this information set. Okay? How? Let us say if player 2 believes that player 1 has taken capital L, has taken action capital L, playing L would give 1, playing R would give 0. If player 2 believes that player 1 has taken action capital R, playing small l would give him 2 and playing small r would give him 1. Of course, 2 is greater than 1. So, no matter which action player 1 has taken, 2 is better off by playing L. So, this equilibrium, this Nash equilibrium O out comma small r is little bit funky, because here player 1 is playing O believing that given a chance player 2 will play R, but we look at it in this particular information set where player 2 has a move, playing R is not optimal. So, we have to think about this we can think of as a failure of SPNE to capture this thing. And why this is happening? Remember, when we are talking about SPNE, what we say that the selected strategy of all players should be rational, not only at the beginning of the game, but also in all sub games. And of course, SPNE is coming from NE. What is the requirement for NE? That all players choose an optimal strategy given their belief about what others are doing. And second requirement for NE is that those beliefs are correct. SPNE goes one step further. SPNE says that players have to choose optimal strategy not only at the beginning of the game, but also in all the sub games. But problem here is, in this particular example, is that there is only one sub game which is equal to the whole game. So, SPNE concept fails to capture this idea that player 2, if given a chance, would never play small r strategy. So, what do we need? We need a new concept, and the new concept should capture that player should be rational not only at the beginning of the game, not only at the beginning of all sub games, but also at each point at which they have to make a choice. And what do we mean by at each point? I have written a term continuation game. Let us pay attention to the earlier example that I gave. Here we can think that this part is not a sub game, but we can think of it as a continuation game, that here the game is continuing in this direction. So, player 2 has to be rational not only at the beginning of sub game, but also in the continuation game, or in other word, player 2 should be rational, or not just player 2, all the players should be rational at all the information set where they have to make a decision. And being rational means that they should be making the optimal choice when it comes to when it is about deciding a particular action. Okay. Now, let us continue with the same example with slight modification. What do we have now? Let me just point out the modification. here we have player 1, here we have player 2, again the same strategies, same actions for player 1. Here payoff remains the same, here we have again the same payoffs. If you notice what we have done, we have exchanged the payoff in R comma L and R comma R. This is the only one modification that we have made. Let me get rid of this. What would happen? Let us look at the Nash equilibrium in this case. What happens to the Nash equilibrium? Again we will repeat the same process. And if we obtain the Nash equilibrium, what are the Nash equilibrium in this case? Let us see. Again here this will be the best response if player 1 believes that player 2 is going to play small l, and what would be the best response from player 1 if player 1 believes that player 2 is going to play small r, that will be to play O. And similarly we have to think from player 2's perspective also. Again let me change the color. And if player 2 believes that player 1 is going to play out, then the best response would be both L and R. If player 2 believes that player 1 is going to play capital L, then the best response would be L, and if player 2 believes that player 1 is going to play capital R, then best response would be small r. So what do we get? Two Nash equilibrium again, L comma L and O comma R, same as the earlier case. But what we have to think now, what we are saying that player 1 in this Nash equilibrium, what does it suggest? That player 1 plays capital L and player 2 plays small l. So let us say player 1 plays capital L and player 2 plays small l, payoff to player 1 is 2 and payoff to player 2 is 1. But why should player 2 play small l at this point? Player 2 is not aware whether player 1 is playing capital L or capital R, because playing R, and if player 2 believes that player 1 is going to play capital R, then playing R would give 2, which is greater than 1. Okay. So the idea is, the focus here is the belief that player 2 should have about what player 1 is doing. We have been talking about belief right from the beginning when we started talking about normal form game. We said that players form belief about what other players are going to do. We said right there that when we talked about Nash equilibrium, that all players choose an optimal strategy given their belief about what others are doing, and second, that those beliefs are correct. But now here that's not good enough. We have to bring that belief in the forefront, because given if player 2 believes here that player 1 is going to play R with with probability 1, then playing small r is better. There is no way to rule out that. So we have to bring that belief system in the forefront. So as I said that in the last example, the player 1 strategy did not completely pin down beliefs of player 2. Okay? At each information set, the player with the move must have a belief about which node in the information set has been reached by the play of the game. As I am talking about that, what we have to say, that precisely a belief system in an extensive game is a function that assigns to each information set a conditional probability distribution over the different nodes in the information set. So what I am saying, basically in this game player 2 should assign a probability to these two information set, because these two nodes in the information set, because these are the only two nodes present in the information set. So we can say player 2 assigns probability small q to this particular node, that when this information set is reached, then this node is reached with probability q, and here this node has reached with probability 1 minus q, and this can be anything. We will of course talk about that later on, that it has to be, earlier we were talking about correctness of belief, here we will talk about consistency of belief. So, why it is important that one strategy profile may be an equilibrium for one set of belief, but it may not be for some other set of belief. So, when we are talking about equilibrium, we have to talk about not only the strategy profile, but also we have to talk about the belief system consistent with that strategy profile being the optimal outcome. By the way, a strategy profile combined with belief system in an extensive game is called an assessment. But before we talk about the equilibrium, let us talk about two important notions, which are sequential rationality and consistency of beliefs. At each information set, the action taken by the player who has a move at that information set must be optimal given the player's belief at that information set and the other player's subsequent strategy. This is called sequential rationality. So, let me go back to the example and it would be clear. Let us say, for example, if player 2 believes that this node is reached with probability q and this node is reached with probability 1 minus q. So, what it means, that if he plays L, small l, then his payoff would be this path will be followed with probability q if he chooses L. So, 1 multiplied by small q, and this path will be followed with probability 1 minus q, and that would be, in this case the payoff is 0. Sorry, not 0 here, that would be the payoff of player 1. Here is again the payoff to player 2 is 1. So, it is 1 multiplied by 1 minus q, and that gives us a total of 1. If player 2 plays R, what would be the payoff with this particular belief system? Q, this small q multiplied by this 0 and 1 minus q multiplied by 2. So, this would be equal to 2 1 minus q. Okay. So, it is very clear that if we are talking about sequential rationality, then what does it mean? Player 2 should play L if 1 is greater than 2 multiplied by 1 minus q, and player 2 should play R if 1 is less than 2 multiplied by 1 minus q. This is followed from the example. So, this is a requirement, that new requirement that we are talking about, that players should be sequentially rational. Earlier also we wanted players should be sequentially rational, but it was not in the forefront. We were not talking in terms of the explicit mention of belief, but now we are bringing belief system in the forefront. Now, after sequential rationality, we also have to talk about consistency of belief. It is not like any belief system is acceptable. The belief system has to be consistent. What does it mean? That at information set on the equilibrium path, beliefs are determined by Bayes rule. This is the same rule that you must have learned while talking about dynamic game in static setting, when you learn BNE, Bayes Nash equilibrium, and it should be consistent with player's equilibrium strategy. At information sets of the equilibrium path, beliefs are determined by Bayes rules and the player's equilibrium strategy wherever possible. Fine. So, these are the two requirements, sequential rationality and consistency of belief. Let us look at the consistency of belief again in the example. Let us say in this example, if equilibrium that we are talking about is capital L comma small l, a belief system cannot have where q is equal to 0. Why? When q is equal to 0, then it means player this particular node is reached, player 2 believes this particular node is reached. in that particular case player 2 should play small r not small l. Why? Because small r gives 2 and small l gives 1. 2 is greater than 1. So, having belief system small q is equal to 0 with this particular equilibrium is not acceptable. That violates the consistency of belief. Okay. So, now we are ready to give the equilibrium definition of perfect Bayesian Nash equilibrium. In short, we call it PBE. Perfect Bayesian Nash equilibrium is a solution concept that incorporates sequential rationality and consistency of belief, as I had already mentioned. Now, a perfect Bayesian Nash equilibrium consists of a strategy and belief defined over every information set. Notice in the Nash equilibrium consists of only strategies. This part, the belief defined over every information set, is the new requirement. So, a perfect Bayesian Nash equilibrium consists of strategies and belief satisfying some conditions, which are that each player's strategies specify optimal action given her belief and the strategies of other player. The second requirement is the belief are consistent with Bayes' rule whenever possible. If we contrast it with Nash equilibrium, what is the Nash equilibrium? Nash equilibrium consists of strategies in which each player's strategy specifies optimal action given her belief and the strategies of other player, and the requirement is, next requirement is that her belief is correct one. So, this is the definition of perfect Bayesian Nash equilibrium. In the next module, I am going to solve the example that we started with, and we will solve some more example so that you understand this notion, this concept in well defined in good manner. Thank you.